going to talk about hurricanes, and as with earthquakes and other things, there's certain case studies I want you to know. We'll be visiting all of these. You might notice that almost all are U.S. examples. This is kind of a egocentric view of hurricanes. I'll mention a few elsewhere, but as you'll see soon, it's clearly not just a U.S. problem. If you look at U.S. events, really we've seen a lot in terms of the most costly events, with Katrina and Sandy being the most recent. So we're going to focus on some of these high impact events in terms of lessons learned. Now, one of the things I point out is that if you look at risk, particularly with respect to fatalities, it kind of depends on what level of fatalities you're concerned with. If you want to know about an event that might kill 10 people per event, then it turns out hurricanes are really not that big a problem. The biggest problem is tornadoes, then floods, then hurricanes, then earthquakes. What we're looking at here is the return period in years, or conversely the probability. But if you're concerned with events that are going to kill 1,000 people, then tornadoes won't do it, floods won't do it. Hurricanes actually are the most deadly. So even more so than earthquakes in terms of just probability of their occurring. So these are major events that are relatively common. Now, the thing that starts things off with a hurricane is warm water. And so the first thing is we want to find out where the warm water is. Warm meaning 27 degrees Celsius or above. We want an area where the Coriolis forces are relatively high. So as you don't want to be on the equator. There's no Coriolis effect of the equator. So you want to kind of move north and south. You want an area that's got enough atmospheric circulation to allow turbulence to begin. And you want to make sure that there's not high-level winds that are going to cut your hurricane off at the top. So there's a limited number of areas where we're likely to see hurricanes form. And it begins with this warm water here. And then if we look at this particular example, I have my pen back now. We're looking at hurricanes that begin as disturbances off of Cape Verdes. Most hurricanes in the Atlantic begin in this area, referred to as the Cape Verdes hurricane tract. And basically, you're looking at warm water and warm air, and that the disturbance starts down here and works its way up, and then basically curves around depending on the nature of this subtropical ridge or this Bermuda high pressure. Okay? And the low pressure system begins as a disturbance, but as a low pressure develops more, you begin to get an internal circulation. Winds are getting greater, so you go from a depression to a tropical storm until finally the maximum winds at the eye or center of the disturbance are at least 74 miles per hour. And so this is kind of the life study of a hurricane, of the Cape Verdes type hurricanes. Okay? And that maximum velocity is going to be right here in the eye wall adjacent to the eye of the hurricane. You've got counterclockwise circulation. You've got ascending air. You're basically taking energy from the warm water, and the latent heat of vaporization is transferring that energy into the atmosphere. And then that energy is released as precipitation. And so the energy that drives a hurricane is the warm water. Conversely, as it gets into colder water or as it goes over land, then it loses that energy and it dies. So we're looking at this track as the initiation track of the hurricanes, and I'll just mention one, Hurricane Andrews. That's a typical Cape Verdes hurricane. Okay, starts off the Sahel, and as we'll see, the weather conditions actually in Africa are one of the factors that determines the frequency of hurricanes in the Atlantic. Now, as I mentioned earlier, the Bermuda High is more or less a steering system for these low-pressure storm systems. And so depending on how extensive that is, the hurricanes may actually end up missing the U.S. entirely. They may come up to the East Coast, or they may come up into the Gulf. There's another set of hurricanes that are generated in the Caribbean. So that's a second type, different from the Cape Verdes. We see those also affecting the Gulf. Okay. So the Caribbean hurricanes and the Cape Verdes hurricanes will affect the Gulf Coast region. The Cape Verdes hurricanes are more typical for the East Coast. And if we look at tracks, well, you can see how these tracks are steered, and you can see how the Bermuda High tends to be the controlling factor. Now, if we take a more global view, we see that same area, the Cape Verdes hurricanes coming up and heading north, okay? But we also see a similar setting off of Mexico, crossing the Pacific and heading north, being steered around this high-pressure system. And we see a southern counterpart. In this blank in here, that's basically the equatorial region. It's the doldrums, and that's where the Coriolis forces are not strong enough to initiate a circulation cell. Okay? Now, when we look at that system, one of the things we note is not only where they're going, but also the fact that these tropical cyclones, if you like, are referred to as hurricanes in the Atlantic, typhoons in the Pacific, and cyclones, pardon me, in the Indian Ocean. So these are the same mechanism. They're just called differently, and so you'll see a little bit of confusion there from time to time. So these are the tracks on the top, a more generalized track at the bottom. And if we look at the relative number, it turns out that what we are focusing on is hurricanes in the Atlantic, some of which are going to impact us, are really a relatively small percentage of the total tropical cyclones or tropical cyclone types in the U.S. Turns out typhoons in Asia are twice as common. We've got some off of the North Pacific. We've got 12% coming in here in the north and south. So there's a lot of activity that's going on that I'm more or less ignoring. But the principles that we're going to talk about with respect to the Atlantic hurricanes largely hold for all of the hurricanes. Now, one of the things I'll be doing in just a moment, I'm going to focus on some case studies here, and those will be some of the few non-U.S. hurricanes that we'll be dealing with. Now, if we want to talk about hurricanes, we need a mechanism for categorizing their magnitude, just as we did with earthquakes and volcanic explosive indices. We need some kind of an intensity scale. So traditionally, we've used the Saffir-Simpson intensity scale, and it turns out that Saffir modeled it after the Richter magnitude scale. So it's basically numbered 1 through 5, and it's characterized by increasingly low pressure, increasingly strong winds, and increasingly high storm surge. Now, one of the difficulties that we have with this system is that it suggests that the pressure and the wind and the surge are more or less linked. But as we'll see, we can have high winds and low surge, low winds and high surge. And so when we think about the problems of predicting the impact of a hurricane. It turns out this system is not as good as the Richter scale. There's a more or less logarithmic change with respect to damage. So you go about 1 to 4 to 40 to 120 to 240. You don't need to know these, but you need to recognize that the difference between a 3 and a 4 is extensive in terms of the amount of damage. The other problem is we tend to use maximum wind speed as the criteria for categorizing these storms, even though there are other characteristics like storm surge and pressure. The storm surge actually is more related to the size of the hurricane, among other things. And so the storm surge is often the most serious damaging impact. And so the Saffir scale is not a really good scale for predicting potential damage. Okay? And it also doesn't consider tropical storms, which, as we'll see, can be some of the major coastal storms and major coastal hazards. It assumes that all hurricanes are more or less alike, and this is something we realize is not the case. If we look at 2 Category 2 storms, both of which had maximum sustained winds of around 100 to 110 miles per hour, notice the hurricane, or rather the diameter of the hurricane force winds with respect to Dolly versus Ike. Okay? As a result, the damage was 1 billion versus 28 billion. Ike was a relatively small storm, but it had a huge storm surge. And so the damage associated with Hurricane Ike, even though it was relatively low wind energy, was extensive because of the size of the storm. So there's been increasing efforts in trying to find an alternative to the Saffir-Simpson scale. Several have been proposed, and mainly Hurricane Ike has pretty much forced this to us because we realize that the scale just is not a good predictor. I can't tell you the scale we're going to use. There are several that are good alternatives, but what I can tell you is that pretty much after Hurricane Ike, meteorologists realized we need a better storm scale. Just as we went from the Richter scale to the moment scale for magnitude, we're going to go from the Saffir scale to some other scale. Okay? Now, because the warm water is providing the energy, we need to heat up the oceans, and so that is going to occur in the late part of the summer. And so not a surprise, if we look at the relative abundance of tropical storms that are and their successors, the hurricanes, we see that it begins in June. This is in the northern hemisphere. And it peaks around September, and then by the time we get into November, the oceans have pretty much cooled off. So we have a hurricane season. Okay? Now in the Atlantic Basin, if we look at the beginning of that season, this is a cumulative frequency diagram. You begin with named storms. A little later, those storms get more highly developed into hurricanes, and then eventually, by September or so, we're getting larger hurricanes. The major hurricanes we typically refer to as a Category 3. Now, having said that, I've already told you a Category 2 or even a Category 1 can cause major problems. So the diagrams that you see here in the discussions that are often in textbooks and even in more recent literature talking about category as being the criteria for major storms is out of date. We just haven't been able to fix that yet. Okay. If you look at the frequency of storm landfall in the U.S., one of the things you look for is red to black. Okay. And what you see is you don't want to live in Miami. You don't want to live in the southern part of Florida. But you've also got some pretty heavy areas here and here. So what we want to look at is how would we determine the risk? I'm sorry, not the risk, but rather the probability of a hurricane landfall. So like floods and like earthquakes, we talk about recurrence interval and exceedance probability. And we do it more or less like you did with the Brazos River data. You'd look for peak something. And let's use tide. Let's use the water level, and therefore we'll be thinking about storm surge and flooding as being the criteria we're trying to match. Okay. Well, we see here in 1900, we had the famous or infamous 1900 Galveston storm. Very high storm surge, about 17 feet. 1915, we had a second one almost as large. And then we have a few little hurricanes that came in here. But basically, 1961 was Carla. And Carla was the first hurricane and the biggest hurricane to hit the area that we had good records of in terms of instrumental records. So we often talk about Carla as the hurricane equivalent, the big one. Okay. In reality, 1900 is the big one, but Carla we know more about. Hurricane Alicia came here, and that was the largest hurricane to hit until Ike. And the thing about Ike is look how much higher the storm surge was. Okay. It was several feet higher than the 1900 storm. Now, a small amount of that is the result of relative sea level rise. But the main thing is we're looking at a Category 2 storm whose geometry was basically made to create a large storm surge. Okay. So what you would do is you would basically plug in all those numbers, that is the height of maximum water level per year, and you would do a frequency analysis. Now, this is a annual recurrence interval, and at the top it would be exceedance probability for areas along the North Sea. And one of the things you might notice is that for the smaller heights and more frequent lower recurrence intervals, they're actually astronomical tides. So we can have spring tides, we can have unusually large astronomical tides, but at some point we go from astronomical tides to storm tides, or storm surges, better said. Okay? And so this particular graph was to try to figure out how common was a 4-meter storm surge that occurred in a storm in, I think, 1990s. Okay? Well, the answer is pretty uncommon. You could look at that, and it's pretty much on a straight line. Actually, they moved it to fit a projection, but it suggests that it is less common than a 100-year flood, 100-year storm, better said. So we would literally just graph these and project to see where that storm might occur. Now, when you do that for hurricanes in the U.S., you can calculate the recurrence interval for landfall within say a 50-mile area. And now we are here, and you might notice that the code is recurrence intervals of, say, 25 to 50 years are in blue. That suggests that the farther north we are, the less common the storms are. They just don't make it that far. The more red you are, the more common it is. And so that reflects hurricanes that come in like this and hurricanes that kind of clip the Cape Hatteras area. And you notice a little high area here. We're sitting right about here. We're looking at about a 10-year recurrence interval, or a 10% probability in any given year of having a hurricane hit pretty close to us here. Okay. Now, we could look at that a little differently and go from North Carolina to Florida to into the Texas coast, and we could look at the 10%, the 2%, and the 1% storm. How high would it be? So in Galveston, we see that there's a 10% chance that there'll be a storm surge of about 8 feet. There's a 1% chance that the storm surge will be at about 14 feet. Okay. Now, again, all of these are based on the kinds of data I just showed earlier for Galveston, looking at the storm surge level and then calculating the recurrence level. Okay. So here we've got recurrence level again, actually exceedance probability, the same thing. The only difference is we're looking at hurricanes versus major hurricanes, category 3 or above. So let's focus on Texas for a moment and see that, again, here in the Houston-Galveston area, we're looking at about 12%, 14%, but only a 4% probability of a large hurricane. Hurricanes, in this case, defined as winds over 200 kilometers per hour. Okay. Here is the percentage of landfall for all storms versus extreme storms. Here it says 7 to 9%. Now, I'm giving these numbers not because I want you to know them. I do want you to understand how they were derived, but I also want you to see they're different. Okay, we're getting different numbers depending on who did it and when it was done. That's not a surprise because unlike floods, where we have just a lot of records, hurricanes are in some ways less common. And so as we get more and more data, the risk, or rather the probabilities are better understood. The most recent data, for example, here from NOAA for the annual recurrence interval is a little different than work that was done in 1975. Yet you'll often see these earlier works done. What's pretty clear, though, is we're looking at about a 10% probability of hurricanes hitting any given year. They tend to have a return period of 10 to 15 years. So we can expect a lot of hurricanes hitting in this region. Okay. Again, these are old data, but for Galveston, again, a probability about 14% of any given year. So hurricanes are clearly, in some ways, a greater risk than flooding. Okay. Now, hurricanes just don't exist on land. It's not just landfall that's an issue. If you're involved in maritime shipping, you'd like to know, am I going to go into a hurricane? We saw the tragic sinking of a merchant marine ship not long ago in the last hurricane scene where the captain sailed into a hurricane. Okay? And so NOAA has looked at the probability distribution in Atlantic. This is for a named storm, and this is the probability distribution for an intense hurricane. So the highest probabilities here are going to be about 6 or 7% in any given year. Okay? So it gives you a better idea of looking at the fact that most of these storms actually are probably not going to hit the U.S. Lower probability of coming in. Okay? Now, here's one of the problems we have with hurricanes, and to a lesser extent with flooding. In order to use the kind of extrapolation, calculation of recurrence intervals that I talked about, we have to assume all things are equal. We have to assume that the previous data were under the same conditions as the future. Yet, we know with floods, if you did it before or after urbanization, it would affect the impact. We know with coastal erosion, if you change the sediment budget, like moving a river, you change the probability of erosion. Well, it turns out that the frequency of major hurricanes varies. So, for example, if you looked at a period from 1950, let's say the 1950s on the left, you had a lot of hurricanes hitting the East Coast. If you looked at a period of the 1970s, 60s and 70s, you don't have any hitting the East Coast. They're all hitting the Gulf. Now, depending on what time interval you used, you might say there's a low probability for the Gulf or a high one, and conversely for the eastern coast. Now, one of the interesting consequences of this is much of the urbanization of the eastern seaboard was during an interval of time, 20 years or more, where there really weren't many hurricanes. Okay. So why is that? Well, let's begin with looking at the variation in wet and dry periods in Africa. In the Sahel, which is the kind of the desert northern part of Africa, you have these wet and dry cycles. Okay? And if you look at the distribution of Caribbean hurricanes during these wet and dry cycles, well, that's kind of interesting because when it's wet in Africa, we got a lot of Caribbean hurricanes. When it's dry in Africa, we don't have too many. In fact, if you look at the 10 wettest years versus the 10 driest years, you've got a significant difference in the distribution of hurricanes in the Pacific. You can also relate that to El Nino. That is, if you look at before El Nino, lots of hurricanes. After El Nino, a lot of hurricanes. During El Nino, not so many. So there certainly is a statistical correlation between the distribution, or rather the frequency of El Nino events, El Nino periods, and hurricanes. In fact, if you look at the frequency distribution with respect to La Nina, the opposite of El Ninos, is in blue, and in red is El Nino. So what it says is, what is the probability of hurricanes during an El Nino period? And you might say, well, there's about a 40% probability, I have to make it about a 30% probability of at least 2 hurricanes or more. Okay. On the other hand, there's a 30% probability of 4 hurricanes if it's during a La Nina system. So if you want to try to predict the number of hurricanes in a given year, the first thing you need to do is to predict, are we in an El Nino period or a La Nina period or in between? When we have El Ninos, we tend to have cooler sea surfaces and drier summers, going back to the wet and dry periods of the Sahel. We're going to have fewer hurricanes. If we have La Nina, we're going to have warm sea surfaces and wetter summers. We're going to have more hurricanes. And I would just skip this, same thing. Now, it turns out the last 9 years or so, we've been in a bit of a drought for large hurricanes of over Category 3. What's the probability of that having occurred? Well, depending on how you look at the distribution, that might be a 177-year recurrence interval for these really long intervals. But the study basically said that this 9 years without a Category 3 is probably just a matter of luck. There's not necessarily any particular significance other than the El Nino system and strong upper winds happen to coincide with low frequency of major storms, okay, at least Category 3. So what we're in the process of doing is figuring out how do we go from simply blindly working out recurrence interval based on just counting the number of years of record to a more robust model of looking at how variations in climate, short-term El Nino to La Nina, will affect global weather patterns, because clearly the frequency of hurricanes is not independent of global weather cycles. Now, if we want to deal with hurricane hazards, we need to look at wind, okay, from up to 200 miles an hour or more, storm surge up to 22 feet or more, waves that could be up to 50 feet high, and the resulting erosion, and rain that could be 40, 45 inches. Now, it turns out that Some hurricanes have high winds. That's the problem. Others it's storm surge, others it's waves. These are related, but we don't always have high numbers in all. So we're going to look at each of these separately first. And let's look at the wind issues first. The counterclockwise movement of air around this depression intensifies as you get closer to the eye. And it turns out, relative to the eye, that wind is the same velocity. Okay? It's just going in a circle. The problem is the eye itself is moving. So the eye is moving at some velocity, which is combined or subtracted from the velocity of the wind. So let's just take this particular example of 160 kilometers per hour, okay, and the storm itself is moving at about 30 kilometers an hour. Okay? Well, therefore, on the right-hand side of that storm, you've got winds that are moving at 160 plus the speed of the eye. So it's at 190 miles per hour, or kilometers per hour. Here you have to subtract the speed of the storm, because the wind on the left-hand side, remember, it's counterclockwise, as seen from above, it's moving in the opposite direction. So it's down to about 128. So we've got about almost a 60 kilometer per hour differential of the winds on the right-hand side moving towards the land, and the winds on the left-hand side moving away from the land. So if we look at that storm velocity, the greatest winds are going to be over on this side. Okay? This being the direction of the storm propagation. And if we take two cross sections, if you took a cross section from front to back, it's more or less symmetrical. Okay? It's a cross section laterally where you see this lower offshore wind and this higher onshore wind. And again, notice the increase in wind velocity, with the maximum wind velocity being at the eye wall adjacent to the eye. Now that has some real significant impacts, not only in terms of wind damage, but also, as we'll see, storm surge and wave damage as well. Okay. Well, this is a picture of wind velocity with a hurricane, actually probably better said a typhoon, Patricia rather, in October of last year. And as we look at it a little closer, we see that counterclockwise spiral. We see the eye, and we see the wind increasing in velocity with the greatest velocities right here. Okay. Now, we also see the eye from the land, or rather from the air, and what we're seeing there, of course, are the clouds and the rain bands. Now, this particular hurricane, Patricia, was the strongest hurricane in terms of wind that we've seen in the Atlantic or Eastern Pacific. And the most recent data suggests it may even be the strongest hurricane ever recorded. Did some damage in Mexico, but it actually wasn't that damaging a storm. It moved fast. It did not have a very high storm surge, even though it had very high winds. And so if we were to look at it, we see again the highest winds here onshore, lower winds offshore on this side here. Okay? So this is the fundamental geometry, the wind patterns of all tropical hurricanes, or tropical cyclones, in this case hurricanes. Now this is the wind patterns for Hurricane Hugo. This line here is hurricane force winds, and notice those hurricane force winds extended way far inland. This is let's see, 50, 60, over 100 miles inland. And the winds over 100 miles an hour obviously did not extend as far, but we had a lot of high winds with Hurricane Hugo, extending a large distance on land. And so one of the big impacts of this hurricane was the destruction of forest cover. So a lot of wind damage, over 100 miles inland, because of the high winds. Okay. Hurricane Andrew, our typical Cape Verde storm, it came on shore near Miami. We had wind gusts of 177 miles per hour, 176 at flight level, 164 before the instrument failed. This is a pretty hefty thing, and so as it turns out, the damage was extensive. Okay. You had whole areas just flattened by the wind, and there are these classic pictures where you got a piece of plywood that's just driven through a palm tree. One of the lessons learned in Hurricane Andrew was that roofs were torn off and the houses collapsed, except where there were hurricane straps. Now, it turns out when you build a house, you can strap the house onto the frame, not just nail it in, but use these straps. Those homes that didn't have those straps were destroyed. Those that did were not. And so the insurance industry very quickly, and also the building community, required hurricane straps for homes built along the Gulf Coast, actually built in any area. And as a result, we've got a building technique now that's made the homes much stronger in response to wind. It's also, though, that as Andrew, the losses were so great that for a long time you couldn't get hurricane insurance because of the large amount of liability that was extended. So wind is a major factor for some hurricanes. The storm surge and storm tide is another factor. Now, we make a distinction between storm surge and storm tide. Okay. The storm surge is the distance above expected water level. That is the super elevation of the water due to the storm. The storm tide is the maximum the elevation of the water. The difference being whatever the tides are doing. Okay. So if you've got, let's say, a 4-foot tidal range, and that storm surge is 10 feet, if it comes in at high tide, the storm tide is going to be 14 feet. Now, it's not a big deal in the Texas region because we are what we call a microtidal coast. Our tidal range is about 1.5 feet. But there are places where the tidal range is 10 feet or more. And so you can imagine the difference it makes if that 10 or 20-foot storm surge is superimposed at high tide or low tide. Turns out Hurricane Sandy, one of the problems was it came in at high tide. Now, if we look at Hurricane Alicia here in Galveston, this is from the Galveston Pleasure Pier area. This line up here is the storm tide. The blue area is the storm surge. The light blue is basically the predicted tidal fluctuations. Okay? So the term storm surge and storm tide are very different things. They approach the same in microtidal areas, but they're often used interchangeably. And so you have to be careful to make sure you know what the reference is. Now, storm surge is a function of a lot of things. The intensity of the storm, duration, speed, size. Okay, all of these are major factors, particularly the wind velocity. Central pressure. The lower the pressure, the greater the water will rise in response to that low pressure. Now, it is a commonly made mistake to say that the reason there's a storm surge is low pressure. Turns out low pressure is a relatively minor variable. Okay. Yes, when you got very low pressures, you do have a bit of a bulge or a rise in sea level. But the main contribution of storm surge is essentially wind piling water up against the coast. How much water is piled up against the coast will depend on the wind speed, the wind duration, the wind area, how slow it's moving. And also, there's an effect of the shape of the coastline. Because if we've got, let's say, a V-shaped coastline, as that pile of water from mainly the wind and lesser extent the pressure difference gets funneled into a more and more narrow space, it gets amplified. And so the shape of the coastline, the width and depth, or the width and slope of the continental shelf, all these are variables. So what we have is a computer model that tries to predict what the storm surge will be. And it uses pressure and size and speed and winds and predicts the track. And they also take into account the configuration, the bays and water depths. And so this is the model we use to predict storm surge flooding, just as we would use another model to predict river flooding. Okay? This is one of the way we calibrate any kind of model like this is we try to match it to historical events. Okay? The better the match, the better we think the model is. So the model's not bad. There's still some areas where we don't do as well as we should, but we're getting better at being able to predict the storm surge, and because we already know the astronomical tides, to predict the storm tide. Okay? Now, because we're going to focus mainly on the effect of wind on storm surge, the greatest storm surge should be where the highest velocity winds are moving onshore. And it should get less and less as we go farther and farther away from the eye as the winds get less. So here is that hypothetical distribution of onshore winds versus offshore winds. And here is the storm surge for Hurricane Alicia. Notice, it peaks immediately to the right of landfall. That's where the eye wall with the highest velocity. So too was the highest super elevation of water. It decreased as you got farther and farther away. The storm surge got less and less as the wind velocity got less and less. There was an abrupt drop in the storm surge on the left-hand side of landfall because the winds there were actually offshore. Okay, so they're actually working to minimize the storm surge. Now, the other thing you might notice is that there are some circles here that are really pretty high relative to this band here. Now, the circles are storm surges in bays. The dark points are storm surge along the open coast. So this envelope is an envelope of storm surge at the coast. Once the surge enters a bay, it can be amplified, particularly as you go towards the end part of the bay, where it kind of funnels down. So you're going to see an increase in the storm surge in the bays, and that's exactly what we saw here. These were areas in the upper part of Galveston Bay. Okay. Down here, you actually had a bit of a set down, and so this would be the backside of Galveston Island. So there's more variation, but there's a greater potential for amplification of storm surge in your bays. Okay. So here we've got Hurricane Hugo again. Remember, it had high winds. I had a pretty high storm surge too, but notice the storm surge over 12 feet is sitting just to the right of landfall and much lower to the left of landfall. Now let's look at the effect of coastal geometry. Here we have a coastal embayment, the Bay of Bengal. The Bay of Bengal has very high tides because tides, like storm surges, are amplified when you've got a funnel effect. So the tide coming in is amplified, so it's the greatest right here. So this is a high tidal area to begin with. Similarly, the storm surge, as tropical cyclones come in, are amplified as well. Okay? So we see some of our worst storm impacts and some of our highest storm surges in settings like this. The Beulah cyclone in 1970 is notable in part for its very high storm surge and high winds, but most significantly because of the high loss of death, or loss of lives. 300 to 500,000 people were drowned in this single event. It arguably is the most fatal geologic hazard that's occurred in recent times, in the last few hundred years anyway. Okay. 20 years later, another storm comes in, a little lower storm surge, but 140,000 people were killed. Now, this is actually for several reasons. Geologically, or you might say oceanographically, this is a bad place to be. You've got this funnel effect. You've got these storm tracks that are coming in. So you're going to have high storm surges. In addition, particularly in Bangladesh, you're looking at the delta of the Ganges and Brahmaputra rivers, which means it's flat and low-lying for large areas. So you've got a lot of people that are at risk by simply living in a flood-prone area or low-lying area. Lastly, it's an undeveloped country, or lesser developed, better said. So there was not a lot of communication, a lot of warning, a lot of evacuation, and so it was prone to a major loss of life. Now, there's a little bit of good news. There was a cyclone in 2013, Category 3 as it hit land. Now, it hit in India here, not in Bangladesh. It was a big storm, high wind. Storm surge wasn't as large as the others, about 4 meters, but only 17 people died. Now, this is extraordinary. And the reasons were basically the disaster preparation arrangements. You don't have this in your notes, but I just found it this morning, are better. And what do I mean by that? Well, first of all, you've got now in India over 1 billion people with cell phones. And even in the small villages that are way out of the way, you've got television, satellite TV. So there is a way of communicating emergency information everywhere very quickly. Okay. They evacuated 800,000 people. It's almost inconceivable to imagine evacuating that many people. But they could do it in part because they could contact the people early. And lastly, they tried to find shelters where if you couldn't evacuate, you could basically hide in place. And the shelters were concrete-built, elevated facilities where you would be above the storm surge and you wouldn't be in a building that was destroyed by the storm surge. So we're beginning to address the problem of decreasing the loss of life. We will probably never really be able to answer the problem of the loss of property. One last example for geometry. It turns out the New York Bight has a geometry somewhat similar to the Bay of Bengal. And what these contours are from 4 to 14 is the amplification of a storm surge up to 21 feet. And now this is a predicted storm surge. based on the geometry of the coast. And this is the predicted storm surge for Hurricane Sandy. It's pretty much accurate. And what we see is that the prediction was pretty much the reality for Hurricane Sandy. And that's one of the reasons why, even though Hurricane Sandy was not a large storm, it had a rather destructive storm surge, the geometry of the coast. Okay. Now let's go back to Hurricane Andrew. Hurricane Andrew comes in, fourth most destructive U.S. hurricane in history. It's a Category 5. It's one of the few Category 5s that's hit on land. Surge of almost 17 feet. Okay. Now I mentioned the fact that the wind damage was very great. Andrew is known for the economic loss, most of which was due to wind damage. Okay. But when you look at landfall over here, here's the contours of the storm surge up to 5 meters. So again, we've got this bulge just to the right of landfall. Okay. Now, the high winds combined with the super elevated water creates very high waves. And so those waves are going to be causing major erosion. Okay. So coastal erosion is a major factor associated with hurricanes. Here's some of the impacts of Hurricane Sandy. This is Hurricane Ike. Okay, so coastal erosion is one of the hazards we need to deal with. And this goes back to what we talked about last week. How do you deal with eroding shorelines? Okay, well, this is one of the reasons shorelines erode. Okay. And it rains. We get a lot of rain associated with this. There's a lot of water in this system. The tracks go on land. The tracks will go all the way to Canada. And so we can have these large amounts of rain. And they're really probably the single most fatal process in terms of lives lost. More than half the deaths in the U.S. are due to the flooding associated, inland flooding, not coastal flooding, associated with hurricanes. With Hurricane Mitch, a Category 5 that hit Central America, the main problems were rains. Rains causing flooding and also rains causing landslides. We talked earlier about how precipitation can be the triggering event for major mass movement, landslides, and loss of life. Well, in this case, the triggering precipitation event is a hurricane. Okay. Looking at of the 56 people killed in Hurricane Floyd, 50 drowned by inland flooding. 200 with Hurricane Diane. One of the things the only thing actually I want you to know about this is that notice Tropical Storm Alicia. Some of our worst flooding events associated with both loss of life and amount of floods and damage actually aren't even big enough to be called a hurricane. They're these tropical storms. We had a tropical storm in 1979 where it rained 45 inches. Okay. It rained over 35 inches with Tropical Storm Allison in Harris County. Okay. It was an unusual event. We talked about it earlier when we talked about flooding, but again, this is one of the ancillary impacts of hurricanes and tropical storms. Here we have rainfall, Hurricane Rita, extending all the way up to the Great Lakes. Hurricane-induced rainfall from Sandy, extending all the way to the Great Lakes again. So, major inland impacts. Okay. Now, I've gone over some of the lists. I want to talk about some of the Texas hurricanes beginning in 1900. And if you look at the state of Texas, you basically see a barrier island system. Long barrier island, the longest barrier island coast probably in the world. Okay, and if you look at the coastal geomorphology of these, we basically have a chain of barrier islands separated by inlets. we have bays and lagoons, and the bays being filled with rivers coming in. Okay, so this is kind of the typical coastline of a barrier coast. In fact, you can imagine we're right there. Okay, now when a hurricane comes in, the first thing that you begin to see, the hurricane approach, well, two things. You see the forerunners. You see these long period waves coming in. They tell you there's a storm offshore. And you begin to see the super elevation of the water, the storm surge. So the first impact will be flooding associated with storm surge. Okay? And you begin to see a little bit of erosion. But once landfall occurs, you've got the highest amount of winds, the greatest storm surge, so you have tremendous amount of coastal erosion. Notice you don't have much erosion here. You've actually got offshore-oriented winds. Rain, the same thing. Rain is greatest on the right-hand side. That's why we call it the dirty side of the hurricane. Okay, so you got more rainfall and erosion. And even after the storm has passed, we have inland rain, inland flooding, and oh, by the way, associated with that hurricane would be tornadoes. And so we can have a significant amount of tornadoes that are so particularly in the right-hand side of the hurricane. Okay. Now, during these big storms, the barrier islands themselves are actually breached. We talked about several of those breaches last time when inlets are formed, which we may or may not try to keep open with jetties. This is just an example of a breach that was then healed by longshore drift in this direction. Okay, we talked about the breakup of Matagorda Peninsula with these hurricane breaches that were subsequently healed after the hurricane. Okay, now when you look at barrier islands, we often talk about narrow versus wide barrier islands. Galveston is a relatively wide barrier island. It's much less likely to be breached like this barrier island. Okay? But having said that, we noted last time that there are areas where literally you will get breaches. And of course, those are the areas we're building on right now. Okay. New Orleans sits here. Yet the biggest port in Texas used to be in Indianola. Well, Indianola was wiped out twice by hurricanes, and they packed up their bags and moved. Galveston became the most important port in the U.S. In the Gulf of Mexico, second most important in the U.S. It was largely wiped out in 1900. And during that time, Houston took over. Houston became a major port city because Galveston was destroyed in 1900. Spindletop was discovered, oil was discovered in East Texas in 1900. And it was Galveston that was going to be the banking and shipping center for that new economy. Galveston was busy rebuilding itself. Houston took over, dredged the ship channel, the rest is history. We're now the oil and gas center of the world. We're now one of the banking centers, and we're now the major port. We talked earlier about this. I'll just go over it very briefly. Galveston was leveled by a hurricane. We don't know how many were killed, but probably 8,000 to 12,000. And I would recommend to everybody that lives here, meaning all of you, read this book, Isaac's Storm. It is a tremendous description of the hurricane and also of the setting of the time and how we dealt with information. Okay, here's the low pressure system, and here's the track. Okay, it was actually up to a 4 before it came on land. Storm surge of 16 to 1,700 feet. We're not quite sure the miles per hour because the wind gauges broke. And we're not sure of how many people were killed even. Notice, it actually continued until finally going into the North Pacific through Newfoundland. Okay. Landfall was down here, southern part of Galveston. And the storm surge, notice that the highest storm surge was actually this part of the bay. Because again, of the water being funneled into this area. Of course, all of Galveston Island was covered with the water. Okay, how do we have this? How do we know this? Well, we modeled it. Okay, so we built the seawall, as we talked about earlier. The rest is history. The seawall basically preserved Galveston from the 1915 storm. It also resulted in the loss of beach that we talked about earlier. Fast forward 61 years, and we're looking at Hurricane Carla. Storm surge of over 22 feet, high winds, a lot of damage. The winds, you had hurricane force winds almost to Austin. You also had hurricane force winds from Brownsville to Port Arthur. Very high wind. We talked about the erosion, but let's look about the storm surge. Storm surge, again, the greatest storm surge is to the right of landfall, lower to the left. The X's are the bays. So notice the highest surge is actually in the bay. On the coast, the highest storm surge was about half as high. Okay. Notice also the location. We saw the effect of the storm surge all the way to the Mississippi River. So these are the areas that were covered by the storm surge with Hurricane Carla in Galveston, remembering that it was 10 feet higher over near Port Arthur. Okay. Hurricane Alicia comes in, much smaller storm surge, about 13 feet. Track was very similar in many ways to the 1900 storm, right around the southern part of Galveston. The eye actually went right over Houston. Okay, and if we look at the area that was flooded, one of the things you might notice is there was an area right here that wasn't flooded. Why do you suppose that was? This is Galveston. That was a part of the island that was raised, remember? When they built the seawall here, the old part of Galveston was raised up to 17 feet. It was the only part of Galveston that didn't flood at that time. If you look at the hurricane evacuation maps for the Houston-Galveston area, they are basically based on the areas that were flooded by Hurricane Alicia and Hurricane Carla. Okay. This was the storm surge we talked about, highest, etc. Now, this looks very similar to that diagram that I showed here for Hurricane Carla. Okay. There's one difference, scale. Okay. The peak coastal flooding at the eye wall for those two hurricanes was about the same. Both, by the way, were Category 3 landfall. But look at the distance that, well, look, first of all, the amplification that occurred up here. And look how much wider the area was of impact. Okay. Hurricane Alicia was kind of a practice storm. We had all the impacts of a major hurricane and a lot of the costs, but on a smaller scale. Okay. Now, if you look at that storm surge and you look at the erosion of the shoreline, maximum erosion right here, and then decreasing as we get farther and farther away. And almost no erosion by the time we get off of Fallis Island. If we look at erosion, the vegetation line versus the high tide line, those are different lines. We talked about that earlier. Look at the extent of washover. Washover occurred throughout the area, but it tended to have these funny spikes, which coincided with development areas. Where you had development, you had the greatest washover. Now, the reason you have the greatest washover where there's development is because when you develop, you remove the dunes. And so what these really are areas without dunes. And so what was clear from this is that particularly the impact of dunes on washovers was huge. Okay. Now over here, there's something funny going on. there's these erosion, but little spikes. In fact, those spikes are pretty large. So if we look at what was going on to the west of landfall, we have these channels that were developed. Isolated little channels. Now, that's a little odd because erosion in general was very minor, or of the vegetation line, rather. We lost a fair amount of the beach, but this is the vegetated portion. And the winds were offshore. Okay? And in fact, what we saw was the bays to the left, the ocean to the right. This is the Greenland. Literally, the water piled up in the bay, moving offshore, and it was blocked by the dunes. So the presence of the dunes basically caused the water to pond up when the water was being pushed offshore. In fact, we have these boats that are pushed onto the dunes by the offshore moving wind to the left of landfall. Okay, not much erosion until we get to here. And these are those spikes that I was telling you about. Major channels, some of which wiped out homes. And so I was trying to figure out, well, why did they occur there and not someplace else? And as I looked into it in more detail, I found out that it's where the access roads were. In other words, it's where the dunes were not. And so here, the dunes basically protected, caused the ponding of the water, except where you had these low dunes or no dunes, where you had the access roads, and that's where the erosion occurred. Because the water was being funneled through these passes. And here's one of my students measuring some of the channels. Notice the area was missing here. There was a house over here. Basically, the water was spilling through those channels. Okay. So the impact of dunes, and better said, the impact of human activity on dunes is a major factor. Okay. If we look at the area here, we saw a lot of, here's an erosion line. This line right here, that was a bulkhead. So you had erosion, house gone. These houses are gone too, and that was actually due to wind. Okay. So there's a lot of wind around. But see, again, here was the old shoreline. Here's the new shoreline. Okay. You can see this was a bulkhead. So was this. Those little concrete bulkheads just could not hold. Again, wind damage here. This house actually was undercut. And so there was enough erosion that the support didn't hold. Minimal washover at the state park because the dunes had been preserved there. And so less washover. Huge washover where the dunes were gone. Okay. Now when you looked at the beach was flattened. There was some erosion of the vegetation line, but a lot of erosion of the water line. And so this is what the beach looked like afterwards. But then much of the sand that was pushed offshore came onshore. And so the beach began to grow until finally it looked about like this. Now then there was a little storm, and it caused deposition of some sand up here. That sand was the feedstock for dunes to start growing. So that was a pile of dry sand, super elevated dry sand, and the beach was wide enough that you could begin to have dunes growing. And this is the post-storm recovery. Okay. So here was the post-storm vegetation line before the dunes and after the dunes. Okay. So what we saw was erosion, recovery, and then after about a year, we go back to seasonal cycles. Okay. So there was, maybe 10 meters of plus or minus, but if you average that out, then you're back to something that is post-storm. Now, this was one of the problems in terms of trying to decide, do you allow somebody to rebuild if they find themselves trespassing on what used to be the state even? Well, it depends. If you're right here, you may want to wait, because it may be under natural conditions those dunes will reestablish themselves in front of you. But then the question is, how long? So based on my studies, at least, it suggests that, after a year or so, if it hasn't revegetated, it's not going to. In areas that were highly eroding, never did reestablish dunes. Because in order to get a dune, you need a breadth of beach, a distance of beach to serve as that feedstock. And if you've got a narrow beach, which is characteristic of erosional beaches, you're not going to get dunes. And putting Christmas trees out there doesn't help. Because what happens is they'll be eroded away in the next storm. Okay. Now, we had Hurricane Rita, big storm, and it was projected to cause a lot of problems. It was supposed to just destroy Houston. Well, it changed. In fact, by this time, it was supposed to be right over Galveston, just to the left of Galveston. Well, as it came on shore, it turns out it veered just a little bit. Initially, it was going to go through right here. Here's Galveston. Here's Houston. We were going to be on the right-hand side. This was the predicted extent of hurricane force winds. Well, what do you do in that case? You leave town. So everybody left town, or seems like everybody left town. Instant gridlock. My neighbors left. 13 hours later, I see them in the driveway. They had gotten 10 miles. Turned around. It turned out that instead, here's Houston, and the hurricane came over here. Made kind of a last-minute turn. Okay. And it caused some major problems in the Beaumont-Port Arthur region. Large areas were flooded. There was an area of some of the beaches. They talk about they were built to be rebuilt. Their prime proximity makes them prime targets. Well, here are all the houses. They're all gone. They were just beveled, the whole island. Okay. In fact, if you look at LIDAR before and after, everything that's red is a missing house. Okay. So tremendous damage there. Okay. The story, well, there are several stories. Don't build on a barrier island. That's maybe a good one. We need to be a little more careful about where the prediction's going to be. We're getting better with that, by the way. And lastly, we've completely changed how we plan on evacuating because of Hurricane Rita. Okay, we're going to evacuate in the next storm, and we did with Ike, differently than we did before Rita. Rita taught us a lesson of how not to get out of harm's way. Okay, Rita also caused a lot of rainfall. Okay, this was the hurricane evacuation map originally, and all we did was simply say the probability of flooding and get the hell out of Dodge. Now, we basically go by zip code, and we say, you guys go first, then you, and everybody else shelter in place. Okay. And as a result, with Hurricane Ike, things worked out a lot better. And let me finish up with Hurricane Ike. We know about that a lot because most of you were here then. Again, landfall occurred right almost at the worst possible place. Okay. Again, at the last minute, Hurricane Ike, they kept predicting it was going to be in the south, moving up closer and closer. Eventually, landfall was just about here. Okay, just around Bolivar Roads. Okay, well, here's the end of Galveston before Ike and Galveston seawall rather, and after Ike. Tremendous amount of erosion of the beach. Okay, sorry. Geotubes didn't help. The Flagship Hotel is no longer there. People could not get out. Houses were destroyed. A lot of erosion along a narrow band and a lot of flooding. Okay. Now, remember though, the erosion is a function of where the waves are, and it's going to be greatest on the right-hand side. Okay. The storm surge was greatest on the right-hand side. We lost houses but they were largely limited to the first couple of rows in Galveston. Okay. If we go to the other side, though, this is Bolivar Peninsula. Bolivar Peninsula was beveled. It was stripped clean with just a few houses left. Okay. The geotubes made no difference. In fact, it may have made things worse. There was one house that survived, and need to say he's a star. And it does say that, you know, if you build a house properly, you may well be able to ride it out with only flood damage. Okay. In fact, that's been the real story of Bolivar. Do you rebuild or not? And the answer is, well, of course we're going to rebuild. Yet look at the difference between to the left of landfall and to the right of landfall. Okay. Had that hurricane come on shore 10 miles to the south, that'd be Galveston that was beveled, and it'd be the ship channel that was a problem. So that really got people's notice, and so now we're talking about, should we build the Ike Dike, a dike that would actually preserve the area, extending the seawall to go all the way around here. Okay, that's a huge issue right now. Would it be better to make it a national seashore, an Ike Dike, something else? Okay, you're going to have to put a barrier here, literally to open and close the ship channel. If you extend the seawall, where are you going to extend it? If you extend it along the shoreline, you will have a beach just like the seawall had a beach, which is to say, no beach. Okay, what's going to happen to a lot of things? A lot of controversy right now. Okay, but this is all being driven by the fact that that E60 line is in the areas with respect to flooding due to storm surge impacts a huge area. And I don't have time to really get into the relative merits. We might talk about it a little more later, but the reality is right now there's a lot of concern, valid concern. Are we going to address this problem? And I'll leave that for you guys to figure out.